Okay, so I'm going to do acid-base equilibrium, and we are going to look at the breakdown of ethylamine, and we are going to try to find the concentration of the hydroxide ion in this solution. So first, we're going to use an icebox. So, an icebox helps us determine the change that we are going to see in the reaction. So, conveniently enough, the equation is right above, so we're going to separate this into three. And so we start off with 0.075 molar of the ethylamine, and we start with 0 hydroxide and 0 of this. And so then we're going, C stands for change, so it's going to be minus X, and plus X, because these are the products of the reaction, so they're going to gain what the reactant will lose, which is the ethylamine. So then the E stands for equilibrium. And so at equilibrium, we know that it will be 0.075 minus whatever was lost. And then you'll have X here for whatever lost was gained on this side. So then, now that we have these, we can plug it into the Kb expression, which is the concentration of the products over the concentration of the reactant. So, we know that the Kb value for ethylamine is 6.4 times 10 to the negative fourth. So that equals the concentration of X times the concentration of X all over the concentration of 0.075 minus X concentration. So we can tell from here that because the Kb value is smaller, that the X is not going to be negligible. So we have to use the quadratic formula. And when you end up multiplying all of this out and getting it all to one side, you're going to have 0 equals X squared plus 6.4 times 10 to the negative fourth X minus 4.8 times 10 to the negative fifth. And so from here, you can see that this is going to be the A, this is going to be B, and this is going to be C. And that will help when you plug it in to the quadratic formula. So you're going to have the B value, which is 6.4 times 10 to the negative fourth, and you're going to negate that. And then you're going to go plus or minus the square root of the B value, 6.4 times 10 to the negative fourth squared, minus 4 times the A value, which is 1, times the C value, which is 4.8 times 10 to the negative fifth. And then that is all going to be divided by 2 times the A value, which is 1. So when all of that is multiplied out, you're going to have negative 6.4 times 10 to the negative fourth plus or minus 0.01387 ... because you don't want to simplify into sig figs yet, because that could change the outcome of your answer. So from here, it's also going to be divided by 2. So first, you're going to, you can either add or subtract, but if you notice from the values that if you subtract, you'll get a negative number, and you want a positive number. So we're going to add the two numbers together and divide by 2, and you're going to get that X equals, which is the hydroxide concentration. So you're going to get that the hydroxide concentration is 6.6 times 10 to the negative third molar. Okay, so you have the first part of what the question asked for. Now they want the pH concentration. But unfortunately, we have OH. And when we take the negative log of the OH, you're going to get the POH of the solution. And we want the pH, which would be the negative log of the H plus solution. But there's a very simple fix. So you still take the negative log of this, and when you take the negative log of 6.6 times 10 to the negative third molar, you're going to get that the pOH equals 2.18. There's a relationship between the pOH and the pH. If you know that the scale for pH is 1 to 14. So you're going to see that the pH plus the pOH is going to equal 14. So now you can plug in 2.18 for the pOH, and you'll get pH plus 2.18 equals 14, which, because of sig figs, pH, when you take the sig figs, you count the two numbers after the decimal point. So it's going to have two sig figs, so when you get to this number, you're going to see that the pH is going to equal 11.82. So you'll have a hydroxide concentration of 6.6 times 10 to the negative third molar and a pH of 11.82.